Good afternoon. Thank you, Mr. Chairman, and thanks ASSA for inviting me and pushing me to give this. Where do I change it? The spacer. Yeah.
You can use this. Use your buttons, and that's the laser.
That's right. Okay, thanks. I will follow this structure here of the talk, and actually we want to just see what I bring in the surveys, the early surveys and the newer ones, and their impact on us. Because we have a lot of advantages from their results, but we also have at the moment some setbacks because they're taking over our niche fields. I will finish then with some examples and mostly light curves.
So if you can put your mic in the mouth, please.
Oh yes, I'm not used to this, so I'm not used to this now. You see one, this better here. Otherwise I take the spacer in, that's fine. I will do it like this. Sorry?
Is it on?
Yes, I'm not used to it. This. The good times of amateur astronomy has been, I think, past. The last 20 years were absolutely stunning. For everything came together for the amateurs who wanted to do something. We got computers, we got affordable, controllable telescopes, CCD cameras, and we got internet access for results from surveys and all kind of informations. And with that we had the full autonomy that we have, because we don't have to motivate for telescope time, we don't have to ask permission, and if I want to observe the moon tonight, I will do so. So it is an important aspect of all this, that we don't have to wait for that. Now the instrumentation in 2011 in my observatory is still the same today. The telescopes are 11 years old, still working to a certain extent. They have the same cameras. I have a proper filter wheel on one of them. The image size is about a third of the full moon. So that's about the star field that I get on an image. And the most important thing is a permanent mount of your telescope. If you don't have a permanently mounted one and aligned properly, you will not use it, or you will not have good results with it. Here's an image of one of them. Now I need the laser. You can see the roof there on top. It is housed in a row of observatory. You see the camera here, and you see the filter wheel, and you see a focuser here, because the focusing system is 3-axis, and one of the motors is faulty really, so it was pulling out of collimation, so I couldn't use it anymore. So eventually I could repair it by using a focuser, get the collimation right again, and this telescope is doing a very good job now still. Now the early astronomical surveys that were, they took a lot of time to observe and compile, and some of them very old, like the plates. They also had limited reach in magnitude and in sky coverage, and they had only specific wavelength range, like the blue color of the photographic plates. And they also had the specific aims, what they wanted to achieve with those. And what is an important thing is the products that came from these surveys. And one of them is the DSS, what the previous speaker has clearly shown. The digitized sky survey, which is a compilation of photographs taken in the north and the south, and which is a very good source for us to plot star fields. Amongst others, is to help to start a supernova searching program. Also, the catalogs that were available on the internet could find for possible cataclysmic variables on the basis of X-ray detections by the ROSAT survey. And then, of course, the catalogs for astrometry and photometry, so you can quantify what you find. Here are some useful websites. that I'm not going to go into, but interesting is the last one is where you can get access to publications, final draft publications. Now the supernova searching project was important for me. I wanted to start that, and I did a deep search and research into the essence of supernova and where they happen and which galaxies were the most likely. So I made actually a top 500 galaxy system for visible search and amended that later to a top 2000 galaxies for CCD search with the system that I had at the time. And I applied those by monitoring certain galaxies so often and with such depth of magnitude. The RC3 is one of the catalogs of the galaxies that I have used most often, which I think is still very valid for now. This image is Galaxy 24431. It's at 80 MPC, which is 250 million light years. On the left, a DSS image, and on the right, an image that I made at the time. So that's my reference image, because they're slightly different. But you can still see both are very much the same. We can see 20 magnitude stars on those. So this is a reasonably deep search. It's just really because this is a relatively far away galaxy to be called a nearby one. Here's the same galaxies in 2005 on 2 occasions. And you can see new stars, one here and one there. There were supernova occurring in that galaxy. And these were the 2 first, I found those, I might say that. The first 2 supernova found this galaxy on record. Probably because, and that's the essence of what we could do at the time, nobody really looked for them. Because this is a very large galaxy. Is better than M83. It's based on it has all the properties of a good producing, supernova producing galaxy. Of course, there is a lot of follow-up studies by groups like the Carnegie Supernova Project. We're very keen to follow up on this in color filters, making nice images, and you see the 2 supernova again on those 2. And even the old one is still visible there, about 6-7 months later. But that was not the end. This galaxy was not done yet. And in 2014 I found my 3rd one in the same galaxy. Galaxy that has never seen any on record before. It's a really good productive galaxy and very much proving that this type of SC system galaxy is very productive. And in 2010, so someone in New Zealand found also a supernova. So that's 4 supernova in 10 years' time. That's one of the most productive systems around. Another example of a supernova is on the right. You can see this one here. It's a slightly subluminous type 1b. The fact was it's a close-by galaxy is about 20 MPC from us, and it was very much followed up. And in 2007-2008, it was gaining momentum that studies on supernova were very important, and large telescopes following it up, amongst others the very large one in Chile. And they only released in 2017 this image of that galaxy, which is used, it's much smaller than ISO 244-31, but it's still a very big one. And they even indicate the supernova there, meaning that these images were made in 2007-2008. They only released in 2012, I think, this image. Now we get the introduction of the later surveys. Some of them have been mentioned today, and I will just show them here. And they have different, although some of them can do a lot, mostly they are only interested in certain aspects. For instance, the Gaia the satellite-based telescope will plot very accurate images of millions of billions of stars with very accurate astrometry and photometry. And by doing other observations later, they will be able to detect small changes in position and brightness. In the process, they have found very many supernova, and unfortunately, they all don't always know what to do with it. ASSA is Ohio State-based initiative with telescopes, small 5-inch telescopes, 3 of them in one group, and they have them in South Africa, they have them in Chile, and they have them otherwhere, also in the northern hemisphere. And they try to make nightly observations of the sky and detect new objects. And they are actually the most productive supernova detecting or discovering system at the moment, despite the small telescopes. And because of that small size, they will always find quite bright objects, 16 magnitude, 17 at most. So they have, they find a lot of things that we can follow up eventually. Now what someone like myself can do is, of course, continue trying to find supernovas, or by competing them, going low on the horizon in the morning sky, or doing a fewer galaxies more often, so that you have a chance of finding less. But we are pushed. If you want to find something, you have to do that, and the result will be that you find supernovas much earlier in the development. That gives far more interest and far more value. Another thing is, of course, to work together with them, which I'm actually doing at the moment. And the third point here is to follow up on their optical transients, because more than half what they find are not supernova, but are erupting cataclysmic variables that we have never known before to be there. They find X-ray sources. They find all kinds of stuff which can be followed up. Now, the way we can follow up on this optical transients is, in my opinion, the best or the most significant one, the most meaningful one, is the time series photometry on the bright optical transients. Time series is where you follow and track a star or an object, and you take measurements continuously through the night, and you end up with 1,000 observations and data points therefore. Another one is the snapshot observations, which we can do. You follow up those transients over time until they get too faint, and you can do filter points. It makes quite good sense to do some of them. Because professional astronomers are not always in a position to follow up promptly or to do so intensively over long periods. So that's actually a niche market, and definitely the time series. Also, I don't know the level of access we have to these surveys, what we can get from them, what we can access. But the fact is that there is a lot of data will be available that you can explore, and you can sometimes mistakes are made. There are mistakes made that are false alerts and so on. An example of a quite recent time series photometry of only 4 hours I've done less than a year ago, and it shows a sawtooth curve typical for an outbursting cataclysmic variable. And the spacing between the top values will give you a hint of the orbital period. It's not exactly the orbital period, it's the superhump period as they define it, but it's only a few percent off. But it gives good science. And especially in a case like this, where you have a similar system, a bit farther away, fainter because of the noise, but you see the same sawtooth curve, but you have also eclipses. And the eclipses are exact distances between consecutive orbits. So we have the actual orbital period and the superhump period, and you can compare those. And by continuing measurement after night, and with other people doing the same thing at other time zones, you will have a very good idea how the evolution is of that other period, so the superhump period. Well, I was not finished yet. I did still find the supernova in 2050. And that one has appeared on the astronomical picture of the day in 2016, I think. I found it quite faint, and it was one of those where I changed my program to do less galaxies more often and very deep. So I found a very faint one, and it was at this position here, but the discovery was far fainter than what you see there. I couldn't show it because you wouldn't notice it. And here the light curve is quite significant because the first point, the first detection was very much before the peak occurred. So it was about 10 to 13 days before the peak, and that's very close to the actual event of explosion, which must have been about here at the time. Now this, I discovered it, but I was not the only one with following up, and a group of Taiwanese observers from the university did also those things. We worked together on a paper, and they actually were the ones that put the astronomical picture of the day on, where they blink those images, and you can see them. This is Eta Carina. Eta Carina had an explosion 150 years ago, and it didn't go through as a supernova. They thought it was, but it was halfway, and I'm very much interested in doing and finding things like that as well. Now, you can only do this for nearby galaxies, and we are still waiting for the supernova follow through of Eta Carina, and we can still wait for 500,000 years. But this is the same galaxy as the 2015 F1. I found, and I was not the first one to detect it, was an independent detection. How does that work now? I want to go back. Here we go. Yes, okay. When I discovered it and I followed up over a week, normally you get a brightening full magnitude per day in the beginning, and it didn't. So it stayed there for 2 weeks, and I had contact with other people that I know are interested in this type of things. And we found indeed the spectrum was showing that it was a luminous blue variable that had a main eruption, something similar to Eta Carina. But what happened then, and I kept on monitoring, of course, because it was bright enough at 17th magnitude, it suddenly just followed through. And instead of waiting for thousands of years like Eta Carina will do, this star actually did explode as a supernova after a couple of weeks. And that is quite amazing. And as expected by the astrophysicists, it would be a type of IC supernova, which is quite bright, and which had is still visible at the moment. It's more than a year ago, it's about 1.5 years ago. It's still visible at the moment, very faint, but this supernova is not finished yet. Talking about amateurs doing work, I do all those things there. I will also do a long-term monitoring of cataclysmic binaries, symbiotic stars, old nova, and see how they evolve, and do time series after the nebular phase. And I also do multi-observation of clusters. But I think the time series photometry of known and newly discovered CVs is still what we can do very much, but will not be easily replaced. The Tarantula Nebula. This is a GPG image. You can't see much, but if you have a fit, you can take off the top layer. You can see inside the heart of the system. You see all these bright stars. One of them is going to explode soon. That is expected. So by taking every 2 months an image, you will see how it evolves, and you will detect variable stars in the system. I do those observations also in V and I, together with my symbiotic stars. There's a lot of clusters that are having interesting behavior by some of the stars. Now this is an image of a cataclysmic variable, and it's a white dwarf here. It's about a half sun mass, a bit more maybe than this red giant. There's also half a sun mass, basically. It could of course be different, but this is a non-magnetic system, and the distance between this sun and this Earth-size white dwarf is about Earth to the Moon, which is actually quite close, and you can imagine that the gravitational pull will be there, and depending on certain conditions, there will be an overflow of material which then strikes an accretion disk and goes onto the white dwarf, and it might lead to eruptions, and then we are ready. That's when suddenly a point what didn't exist yesterday will show up on ASSA detection, and they will see there's something there, and often it's something like that. Magnetic systems are similar to the non-magnetic system in the way that they eventually end up have material ending up on the white dwarf, but instead of circling around in a accretion disk, they will really dump it on one of the poles, or on both of them. Again, time series photometry on those. This is actually a recipe I have for how to do it, but if you want to discuss it afterwards, but I'm just continuing because of the time. Here is 8 hours time series of the polar, a very interesting star that we have done with CBA in 2000 hours, with several observers north and south. We got a very long, interesting light curve where we saw that the eclipse would change in depth, even with the same filters. And suddenly there is some progress there. And look at the distance here, there's a 2.5 magnitude change in, let's say, 15 minutes. So this thing is very active. Again, snapshots, the alternative to time series is snapshots, taking an image every week or every month, and taking several images, stack them, and have a deep field of that star and its neighborhood. Here, I give you some line curves here, and this is 16 years of BB Doradi. It's known as an ogre-like system. And the normal situation of this star is that it is bright, that it is like an outbursting cataclysmic variable. It's around 14 magnitude. But once in a while it will lose accretion or something happens, and in certain periods it will stay away from the 14. It will always be less bright than it's supposed to be. But the normal situation is a bright one. Now what with these years monitoring, I want to continue several years still, because I want to see if this space will be the same as that one. It's about the same as here. So are these states of normal quiescence and of change, are they equally distant? And so we need many more years, and I hope the surveys can help us there. This is a similar system, but it's most of the time in a faint stage, and it will then move cycle at times, and being quite nervous, coming bright and going off. Again, we have a space here. Is there an underlying reasoning why they would be like they are? And long enough observations will help us there. An interesting system is V104T Centaurus, which I've been monitoring quite some time, and by doing many measurements at the time, I was actually able to help assist in giving that period to the database. All this, if you go back so many years, you see the name change always. You have always another name. And then once it is covered by observations and the variabilities group, and you will get this. Now this is a polar, and that's a heavily magnetic CV, and this is time series for 6 hours. Now the period of the system is about 5 hours, and you can see the period is that here, and from here on we'll do the same as there. Now what is interesting here is that this magnitude change about 0.6 at most. So if the system is the same, it will be within 0.3 either side of this magnitude. Now if you do snapshot of this, you will take one here or you take one there, you don't know when. So if you do snapshots, you can be 0.3, 0.4, 0.5 out from the previous night, even if the system is the same. With that in mind, we can look at the 16 years of the stars, taken every week or every month or whenever it was time, and you can see indeed that most on the top are within half a magnitude. So we have a quiescence there, but we see outbursts and eruptions here and there and big ones here. So this system is not always at rest. It is sometimes getting an extra accretion or whatever that causes it to get brighter. But the interesting thing here is that the trend of the quiescent magnitude shows that it has changed half a magnitude in 16 years. This might be significant. This is a similar star, also it's a Taurus. It is an intermediate pole, so the magnetic strength is less, but it's still a magnetic CV, and you can see since the beginning here how its average magnitude has changed enormously over the years, getting brighter here and going back, and it seems to start a new cycle here. And the thing is, are we going to see that repeated every time? So we need far more observations of that. There are also outbursts that are visible in this branch. While on that branch you will see periods where the accretion must have been less. So initiating the faint state here. But it is definitely picking up because I have data points that are not going to occur. Here is an example of polar with a red dwarf star which is depleted. Was mentioned earlier that the other star is nearly out of gas. I mean, it's finished. And we will expect that outbursts like these will be less and less common. But we're talking about thousands of years still. This is only a small shot in time. Other one, but I have many of those curves, but I rather skip them, and I'd rather show you what I would consider my main project since 2010. And it's amazing to know that this type of stars, set Andromeda stars, are not monitored by nobody else, even in the north. I've tried to find out. The light curves that I have, which are 12 years, more than 12 years old in the visible and less in the infrared, are unique in the sense that they show things that were not known. I can show several systems that were wrongly IDs. I found the right one. I found ecliptic systems that were not known to be. And I found improved ephemerides of others. And I found that there was a symbiotic nova clear from my data. These are schematics which might not be actually accurate. But our Aquaria is known to have a jet stream and a red. Yeah, okay. The distance between the star and the white dwarf is between the Earth and Pluto or something, or near to it. So these are a huge system, and there's a big inertia to be expected. This one looks like a planetary nebula, and this is a light curve of 14 years of a yellow symbiotic star. It's a yellow supergiant, and the light curves in the visible on the top and the infrared on the bottom are similar. Probably because the yellow star contributes quite a lot on this. But that's not always the case. Now this is visible, and I see a light curve of an old nova at a telescopium, which is a symbiotic star. And you can see how it's still fading in the visible from the outburst. But you see here in the infrared, we see the red giant star with the light of its own. It is pulsating, and when it pulsates, it will reach a maximum magnitude here, which is it's bigger and it is wider, and therefore it will also add to the visible light curve, which it doesn't do otherwise. So this is actually, if you have only one wavelength, you will not be able to find out about this. So it is important to use different wavelengths, and if you add X-rays to it, you will probably get more of it. Recurrent nova 745 Scorpio. Monitored for a long time is unfiltered, but I started 10 years ago with filters. And you can see a high state here and a low state there. And what's interesting is that the recurrent nova explosion happened during the faint state. That's quite interesting to me. And here we have the infrared light, which shows 100-day periodicity. And here is to stop the symbiotic nova with 13 years of observations, nice and just last year it started to get brighter. And even this is the period gap, so this is late. These are up to last week data, so you see it's still brightening, and it's about 12 magnitude visibly in the infrared. Yes, that's something else. Okay. Thank you. Sorry for the time.
Thank you very much. Time for a quick question. Everybody's hungry. Case, do you want to say a few things about tonight?
Thank you very much. It was very good.
Thank you.